So star and delta connection. So next one we are going to see about three-phase loads. So then the load, since you have three windings, you can have three-phase loads. Also, loads can be connected across your three windings so that it can drive your load. So the two three-phase loads are possible. One is the star load, another one is a delta load. Okay, from the diagram you can see star is also called as Y. It is looking like an inverted Y, right? So star is called as Y connected network, and delta will look like a triangle. So it is a delta load. And each arm of your star and delta, you will have the impedance Z1, Z2, Z3. They are called load. So three phases can be used to independently supply power to three different loads. So you can connect three different loads simultaneously across the three windings. So the loads can be connected either to form star or delta. So depending on the type of load, two connections are possible. One is star, another one is going to be delta. So see here in the load, if all the loads are same, if Z1 equal to Z2 equal to Z3, both in resistance and reactance, if all the R values and the X values are same in the load throughout a star or delta connection, that load is called as a balanced load. Okay, balanced load means all the load values will be same. The resistance values will also be same. The reactance value will also be same. So that is called as a balanced load. Okay, that is called as the balanced load. So loads which are carrying balanced. If you're having a balanced load, then the currents and voltage will also be balanced in a particular network. If you're taking star or delta, if the load is going to be balanced, then the current and voltage will also be balanced. So three-phase motor is a balanced load since it has three identical windings. So when you are going to supply a three-phase voltage, the currents are also going to be balanced. So remember, in a balanced load, all the currents and voltage are also going to be equally distributed across the windings. Okay. Any doubt you have so far?
No, sir.
Okay.
No, sir.
Okay. Now we see about star connected systems. You know how to connect star. See here, R dash, Y dash, and B dash. You write the windings. Connect all the finish ends to a neutral. So connect all the finish ends to the neutral. Connect all the start ends to one side of the load. That is how it's star connection. So just understand what I am saying. All the finish end connected to neutral, all the start ends connected to your loads L1, L2, L3. Other ends of load are connected to a terminal M, and this M and N are shorted. So they both act like neutral. Okay, between N and M, total current will flow. That is going to split between IR, IY, and IB. Okay, between the neutrals, the total current is going to flow. That current is going to split at this node into three equal currents, IR, IY, and IB. Okay, that is going to be the arrangement of a star connected system. Okay, so this is the diagram. So this diagram is very difficult to understand. So what we will do, we are going to redraw this diagram in a different way. So we are going to redraw this diagram in a different way to get this. So see here, R dash, Y dash, B dash connected to a common point N. Across R, Y, and B, I'm going to connect my loads L1, L2, and L3. So this is going to be my R, this is my Y, and this is my B. Across R, you see, I'm connecting L1. Across B, you see, I'm connecting L3. Across Y, you see, I'm connecting L2. So these two diagrams are one and the same identical diagrams, but they are drawn in a different way for understanding, for better understanding. Okay, otherwise nothing. Otherwise, it's going to be nothing different. So the representation of the representation of the windings are the same in both the diagrams. One of here the importance is given to windings. Here the importance is given to the neutral points N and M. So both the neutrals N and M. Here we are connecting the same N. So this neutral is going to be same for both the windings as well as the load. Okay, so this is going to be same for the windings as well as the load. This is a star connected three-phase system. So see the steps, as I said, is shown here. Join all the finish ends to neutral, join all the start ends to load, and another end of load is connected to M. So NM is going to provide the necessary closing path for the current to flow. See, in this star connection, it is called as a four-wire system because three windings plus one wire is needed for the connection between the neutral. So it is called as a four-wire star connected system. Why four wires? Because I am going to I'm going to give one connection between the two neutral sides. So it is going to be called as a four-wire star connected voltage system. And that n point n is called as a star or a neutral point. Okay, so it is called as a neutral point, which is required to carry the total current. So the three-phase motor windings are connected to the terminals R, Y, and B. So if you're connecting the simple gadgets like lamps or heaters or microwave ovens between the lines to act as load, they will be supplied the current by the windings, and they can be operating. You can operate the load in across each of the three windings simultaneously. The total load will be distributed equally across the line. See, if a lamp is going to consume low current, if heater and microwave ovens are going to consume large current, means even though the current consumption is going to be different, when you consider the star connected system, the load will be equally distributed across the line. So the load currents are going to be identical. Only thing, they will be differing by 120 degrees. The current's magnitude is going to be same. They are going to differ only by 120 degrees because of generation of the rotating magnetic field. The same thing what we done here for voltage, right? The same thing is done here. Please look at it. Just look at that equation and let me know if you have any doubts. I am pausing here for 10 seconds. Okay. Just look at that equation and addition. When you add all the three currents, you'll be getting zero. Just look at the equations and understand. I'll just be back. Similar to voltage, I am writing the current equation. Also see here, one is sine omega t, one is sine omega t minus 120, one is sine omega t minus 240. So if you are going to add all the three currents, you will be getting the answer as zero. This verification we have done already. You can do it if you want again by using sine of a minus b and sine of a minus b formula. Sine of a minus b is sine a cos b minus cos A sin B, right? So if you apply that formula here in the second and third term, you will find that all the terms will get cancelled. So you will get the answer as zero. Okay. So in star connected system, total current will be zero. That's why neutral is a point where the current is going to be zero. So all the currents will be, when you add all the currents, see here, IR plus IY plus IB is going to pass through the neutral, which is going to be zero. It is going to split equally. So when all the currents come and meet at neutral, it is going to be zero. That is the understanding you should have. Okay. Now we are going to see what is a star connected three-phase system. So I'm going to connect is the three-phase winding to a three-phase load. Both are star type. See here, the windings are also of star type. The load is also of star type. So across one winding, you will have a load. So R dash will have a load Z, Y dash will have a load Z, B dash will have a load Z. And the conductors which are going to join your generator and balance load is called as line conductors. So three line conductors L1, L2, and L3 are used. It is a balanced load. So see, the value of Z is same everywhere. So it is a balanced load. The domestic load will always be unbalanced load because you will not be running the appliances all the time. You will not be switching on your heater all the time. You will not be using your air conditioner all the time. So domestic load is always an unbalanced load because The load is not same at any point of time. The load is going to be variable always. Okay, but industrial load, since you are going to run the machine for a constant amount of time, industrial load can be considered as an example of a balanced load. So unbalanced load means it has three different currents in all the three phases, but when you add everything, it will naturally be zero. So that condition will be always satisfied, and because the voltage across the loads gets adjusted, and the sum of the currents will be zero. For an unbalanced load, that point n is called as a neutral shift, or it is called as floating neutral. So in normal balanced load, you call it as star or neutral point, but in unbalanced load, because the impedance is not same at all the points, but if when you add the current, it still becomes zero because the voltage gets adjusted across the three terminals. Sum of currents will naturally be zero. So because of this reasoning, you don't call that n to be the actual neutral. You call it as a neutral shift or floating neutral. Floating neutral means it is not the exact neutral because the loads are not same. So this is an example of a diagram where you are having both domestic load and industrial load connected across your three-phase voltage system. So domestic load will be an unbalanced load, and industrial load will be a balanced load, and both domestic can be star or delta depending on your choice. Since because it is stored in a star network, you need not have a star network. You can have delta connected load also to your star network. That also can be possible. Okay. So the potential at the neutral point is still non-zero because it depends on the load impedance. So since you are not perfectly adding all the currents and making it as zero, so that potential, the neutral point in case of an unbalanced load, sometimes it may not be non, sometimes it may not be zero because it depends on the load impedance. Because one four phase voltage may become larger than the other phase voltage, leading to equipment damage. So when you have over voltage, equipment will be damaged. When you have under voltage or low voltage, the equipment becomes undesirable. So normally we are not using unbalanced star controlled loads on a three-wire three-phase system. So that is the reason why we are not using unbalanced load. So unbalanced load means it will lead to change in current and voltage. So the current is reducing means the appliance will not work. The current is increasing means it may damage your equipment. So always we look for balanced load only. Always look for balanced load only. That is going to make your system safe, and the neutral condition is also satisfied.